Good evening. Tonight we have with us Dr. Lawrence Weinstein. He's a physics professor at ODU, and he's also a member of our experimental nuclear physics group here at JLab. He has published 2 books about guesstimation. His latest one, Guesstimation 2.0, Solving Today's Problems on the Back of a Napkin, came out in October, I think. So if you would please give a warm welcome to Dr. Lawrence Weinstein.
Okay, thank you very much. What I hope to be able to do today is to show you why guesstimation is useful, why it's interesting, some results we can get out of it, and most importantly, how you can land that job with Google. So, why do we estimate? Well, we estimate because we're always bombarded by large numbers. Our deficit's $1 trillion, the gross domestic product is $16 trillion, we each make 100 cubic feet of trash a year. What do these numbers mean? Which ones are important? Which ones are unimportant? And typically when we are asking a question, it's because we want to do something with the answer and to make a decision to do something or not do something. And that means that when we estimate, the answers can come in one of 3 categories. It can either be really large. Oh my gosh, I can't possibly afford to do that. I'm not going to buy whatever it is. Really small. Oh, that won't take any time at all. Of course I'll do it. Or somewhere in between. And so when we're estimating, we'll try and get the answer to within a factor of 10. And most of the time, that answer will either fall in the too small category, so what to do is obvious, or the too big category, so what to do is obvious. And it's only when the answer falls in the middle that estimation's not good enough. And then we have to do more work. So the other thing is that Google and companies like Google use estimation questions in their job interviews. And so if you have plans to work for a company like that, and you can estimate, that'll give you a leg up. So, how do we estimate anything? Well, step 1, write down the answer. How long does it take a pumpkin to fall from the top of a 10-story building? A few seconds. Well, if you don't actually know the answer, you can certainly bound the answer. Well, I know it takes more than 1 second for that pumpkin to fall and less than a full minute. So it has to be somewhere in between. Then, what we do with those bounds, and this is going to be the most complicated mathematics tonight, is we take what's called the geometric mean. That means we take the square root of the product of the lower bound and the upper bound, or we can just say, well, we're just going to average the powers of 10. So, how many clowns can fit in a Cooper Mini? I don't know, but it's certainly more than 1, and it's certainly less than 100. And so when I take the geometric mean, I'm going to take the square root of 1 times 100. That's going to be 10. And I'll estimate 10. What's the good of that? Well, it ensures that my estimate is within a factor of 10 of the final answer. And so it'll be equally far from the high or the low. And that's important when we get to step 2, because in step 2 there are some problems that are too complicated. You can't just write down the answer. You have to break it into pieces. For example, how many piano tuners are there in Hampton Roads? Well, I don't know. But I can estimate how many pianos there are. And I can estimate how often a piano gets tuned. And I can estimate how long a piano tuner takes to tune a piano. And then when I'm done, I can multiply all those estimates together and get my final product. So if I can't write down the answer, I'll break the question into smaller pieces, and for each piece, I'll establish these upper and lower bounds. And so the point here is that we're going to be incredibly sloppy with arithmetic because we're just trying to get the answer to within a factor of 10. So we need to make arithmetic easy. Million, 1 followed by 6 zeros. A billion, 1 followed by 9 zeros. A trillion, 1 followed by 12 zeros. Here's a $100 trillion bill from Zimbabwe. I'm not great at counting. And so what I'm going to do is I'm going to use scientific notation so I don't have to keep writing down lots of zeros, keeping track of lots of zeros. I'm just going to use scientific notation. So 3 followed by 11 zeros, I'm going to write as 3 times 10 to the 11. The 11 is the number of digits after that first one. The 3 is the leading digit. And because I'm estimating, I'm only going to keep 1 leading digit. So now, when I do my arithmetic, 3 times 10 to the 4th, 30,000. 2 times 10 to the 5th, 200,000. Rather than counting the zeros and multiplying it out, it's easy. It's just I take the two coefficients, 2 times 3, the two exponents, 4 and 5, and so it's 2 times 3 times 10 to the 4 plus 5, so the answer is 6 times 10 to the 9. That's the arithmetic we'll be doing tonight. If you can do addition and multiplication, and it's only one-digit multiplication, you're good. The exponent's the important number. It's much more important that this number is 10 to the 9 than that the leading digit is 6. So when we do arithmetic, 3 times 3, that's 10. 9 divided by 4, that's 2. Square root of 10, that's pi. I like pi. So we'll be doing simple arithmetic. And again, one of the things that happens, these are just some things that were in the news today. We're spending $250 million to Egypt. The sequester will cut $85 billion. Our budget deficit this year will be $1 trillion. What our eyes do is they look at the 250, the 85, and the 1, and those other things are illions. But those illions are the really important parts. So let's look at the difference between a million, a billion, and a trillion. One day, 24 hours, 60 minutes in an hour, 60 seconds in a minute. That's about 10 to the 5th seconds, 100,000 seconds. That means that 10 days is about 1 million seconds. And that 10,000 days is about 1 billion seconds. Well, 10,000 days is about 30 years. So the difference between 1 million and 1 billion is the difference between 10 days and 30 years. It's kind of a lot. A trillion is 30,000 years. Let me put this more graphically. This is from XKCD, one of my favorite webcomics. Headline from a few years ago, bailout, $170 billion, bonuses, $165 million. Wait a minute, we're bailing out Wall Street and they're giving all the bailout money to bonuses? No. You've got to put it all in the same units. Bailout is $170,000 million. The bonuses are only $165 million. So it's a tiny fraction. And the difference between 1 million and 1 billion is the difference between a sip of wine in 30 seconds with your daughter and a bottle of gin and all night. It's a lot. Factors of 1,000 are big. So, important questions. How many people in the world are listening to you don't care about that, picking their nose right now? How do we estimate that? Well, you can start from how much time does the average person spend picking their nose? And, everybody picks their nose. So what we can say is that the fraction of time the average person spends doing an activity is equal to the fraction of people doing that activity now. So if we can estimate how much time one person spends picking their nose every day, then we know how many people are picking their nose now. So how much time do people spend picking their nose? Well, it's going to be, I don't know the answer, but it's going to be more than 1 second, and it better be less than a couple minutes. So that means it's between 1 second and 100 seconds. The geometric mean of 1 in 100 is 10, so 10 seconds a day. Well, we've already calculated that there are 100,000 seconds in a day. So 10 seconds out of 10 to the 5th is a part in 10 to the 4th. So 1 in every 10,000 people in the world, on average, is picking their nose as we speak. There are 7 billion people in the world. So that means there are 700,000 people picking their nose right now. Is that an exact number? No, but it's probably not too far off. It's within a factor of a few. And that's how close that we're aiming to get. We're aiming to get within a factor of a few. Environmental questions. How much trash do we make a year? Well, I don't really know, but I know how much trash I make. And it's more than 1 pound a week and less than 100 pounds a week. So that means, assuming that I'm typical, which could be dangerous, is that it's 10 pounds per person per week. Well, let's double it to include businesses. That's 20 pounds per person per week. There are 52 weeks in a year. 20 times 52, no, 20 times 50. Forget the 2. 20 times 50 is 1,000. So that means that there's 1,000 pounds of trash per person per year. That's half a ton. 300 million people in the United States. You have to know a few numbers to be able to estimate. It helps to know the population of the United States. And we'll come up with some other numbers here. that means that the United States makes 200 million tons of trash a year. That's actually remarkably close to the real number. So the question now you have to ask is this a lot or a little? And the answer, of course, is compared to what? Well, let's think about where we can put it. I live in Virginia Beach. Virginia Beach has the very first Mount Trashmore ever erected in the United States. We took all our trash for many years and we piled it up in a big hill. And when we were done, we put dirt and grass over it, and now it's a very nice park. So, how much landfill space would we need for all of our trash for the next 100 years? That's going to be a lot of trash. Because it's 200 million tons a year, there's 100 years. But now we need to figure out how much space does trash take up. So now we need another number. The density of water is about 1 ton per cubic meter. Density of steel is about 10 times that. It's about 10 tons per cubic meter. And you figure that trash floats. So it's going to be less dense than water. Well, how much less dense? I don't know. Let's figure, I've got a 2 here. So I'll just put a 2 down here. So it's 5 times less dense. So instead of 1 ton per cubic meter, which is the density of water, we'll assume that trash, even if it's compacted, is 0.2 of a ton per cubic meter. That means that we need 10 to the 11 cubic meters. 100 billion cubic meters of trash in the next century. Where can we put it? Well, how tall can we make our landfill? Mount Trashmore is 62 feet above sea level, so it's 20 meters tall, because a meter is about 3 feet. So let's make it 5 times bigger. Let's make it 50 times bigger. So instead of, we'll make it 100 meters tall. Because we can make it more than 10 meters tall, that's 30 feet. It's going to be less than a kilometer tall, so we'll make it 100 meters tall. So if it's 100 meters tall, then that means that the area is 1 billion square meters. 1 billion square meters. Ooh, that still sounds like a lot. But we don't measure land in square meters generally. We measure it in square miles or acres or square kilometers. And so there's 1,000 meters in a kilometer, which means that there's 1,000 times 1,000 square meters in a square kilometer. So there's 10 to the 6 square meters in a square kilometer, and that means that the area we need is 1,000 square kilometers. Now this is for all of the trash generated by this country for the next 100 years. Okay, 1,000 square kilometers still sounds like a lot, but it's the size of Virginia Beach. I don't want to put it in Virginia Beach, mind you, but that's all the area of Virginia Beach or Los Angeles. And what does it look like? Well, here's a map of the United States. There's our landfill. Anybody got a problem with that? So landfill space is not the problem. It's a big country. We've got plenty of space. So what we learned from estimation is that the space for landfills is not a problem. And this is an example where, suppose we're off by a factor of a few in our estimates. Who cares? If that dot's 3 times bigger or 5 times bigger, it doesn't really change the conclusions. If it's 5 times smaller, it doesn't change the conclusions. And all we started from was, how much trash do you take out every week? Okay. Big thing, we drive gasoline-powered cars, and they're trying to get us to buy these wonderful plug-in cars so that the car itself does not have any emissions from the tailpipe. Okay, but if that's such a good idea, why are we all still driving gasoline-powered cars? Well, the difference is that with a car, you need a store of energy in the car. With a gasoline-powered car, that comes from the gasoline. With a battery-powered car, that comes from the battery. So, how much energy does gasoline hold? Now we're going to get into some chemistry. I'm not a chemist, I'm a physicist. So we've got coal, that's just carbon. We've got methane, natural gas, that's CH4. And so gasoline has more hydrogen than coal, less hydrogen than natural gas, and so we'll just call it CH2. Now what happens with gasoline is that it's a long chain of carbons with a hydrogen above and below, but on average there's about 2 hydrogens for every carbon. I'm not going to bother getting more precise than that. So when you burn gasoline, what's happening is that CH2 is combining with oxygen, and The C goes to CO2, the H goes to H2O, and there are two chemical reactions there. Now the CH2, carbon has an atomic mass of 12, hydrogen has an atomic mass of 1, and so you've got 14 grams in a mole, and so that means that a kilogram contains 100 moles. 70 if you're being precise. I'm not being precise. So a kilogram contains 100 moles. So now we have to figure out how much energy you get from each chemical reaction. Now, again, I'm a physicist. I'm not a chemist. But what I've got here is something that does a sophisticated chemical reaction to turn chemical energy into electrical energy. It's a battery. This battery puts out 1.5 volts, approximately. So we'll just take that number, 1.5 volts, and we'll say that 1.5 volts is what you get from a chemical reaction. Except that now we have to get a little more complicated. It's one electron moving through a potential difference of 1.5 volts. That gives you 1.5 electron volts. The energy I have in a kilogram, I've got 100 moles in a kilogram. I've got 6 times 10 to the 23rd, that's Avogadro's number, molecules in a mole. I've got 2 reactions, because I've got CO2 and H2O, so I've got 3 electron volts. And then I need one more conversion factor that's not too commonly known, but there's 1.6 times 10 to the minus 19 joules in an electron volt. What does that mean? Well, it's going from electrons per second to amperes. So it's how many electrons in a coulomb, and it's just a conversion factor between joules and electron volts. So when we multiply this all out, well, 6 times 1.6 is 10. Oh, that's easy. 10 times 10 to the 23rd is 10 to the 24th, times 10 to the 2 is 10 to the 26, times 10 to the minus 19, 26 minus 19 is 7. I get 3 times 10 to the 7 joules per kilogram. Reality is about 4. So how do we get this? Well, we just made an incredibly simple assumption about gasoline, that it's got more hydrogen than coal and less than natural gas. We said that the energy per chemical reaction is the same as you get from a AA battery. And that's it. From that, we get the energy density of gasoline, 3 times 10 to the 7th joules per kilogram. Is this a lot or a little? I don't know. We don't have anything to compare it to yet. Electric cars are brand new. This one is only 116 years old. So, why aren't we driving them? Well, let's look at the energy density of batteries. How do I know the energy density of a battery? Well, you pretty much all used a flashlight. And so think of a big flashlight with an incandescent bulb. It puts out probably about as much, puts out a whole heck of a lot less than a 100-watt light bulb does. And so it's probably between 1 and 10 watts of light. How long does it last? Well, if you leave it on, it'll last more than an hour and less than a day. And so that means that if I've got a D-battery powered flashlight that puts out more than 1 watt and less than 10 watts, so the geometric mean of that is 3 watts, lasts for more than an hour, less than a day, well, 1 hour and 25 hours, geometric mean of that is 5 hours. So stored energy now. So power times the time. 3 watts times 5 hours times 60 seconds in a minute times 60 minutes in an hour. So there are 4,000 seconds in an hour. Yeah, I know it's 3,600, but just makes the math more complicated. 3 watts times 5 hours is 10 watt hours. That's going to give me 40,000 joules. So that's 40,000 joules stored in a D battery. What does a D battery weigh? I don't know. There are probably a few D batteries in a pound. So we've got a few D batteries in a pound, which would be 5 to 10 D batteries in a kilogram. That's going to give us 300,000 joules per kilogram. So we had 3 times 10 to the 7 joules per kilogram for gasoline. We've got 3 times 10 to the 5 joules per kilogram for batteries. Batteries have 100 times less energy per kilogram than gasoline, which means that if you want to replace the gasoline in your car with a battery, you need something that has 100 times the mass. So let's say your typical car gas tank has 10 or 20 gallons. 10 or 20 gallons is between 40 and 80 liters because there's about 4 liters in a gallon. Liters about a quart. 40 liters means you've got a mass of 40 kilograms, which is about 80 pounds. So you've got about 80 pounds of gasoline in your gas tank. That means you need 8,000 pounds, 4 tons of batteries. Not going to happen. That's not quite fair. You win a factor of 4 in efficiencies. You only need 2 tons of batteries. But still, your battery has to weigh more than the car if you want the same range as a car. So that's a problem. Well, let's look at the second one. When you fill your car, you drive up to the gas pump, you put in 10 gallons of gas. Well, so you put in, figure 12 gallons, it's about 50 liters. It takes more than a minute, less than 10 minutes, or more than 10 seconds, less than 1,000 seconds. It takes a couple minutes. A couple minutes, 2 minutes is about 100 seconds. So that means that you're transferring power is energy divided by time. So that's going to be 3 times 10 to the 7 joules per liter for gasoline. You're putting in 50 liters of gasoline, and it takes you 100 seconds. That gives you 10 to the 7 watts. 10 megawatts. Your typical power cord at home can transfer about a kilowatt, which means that you need a really, really, really thick power cord to charge up your battery at anywhere near the speed that you can put gasoline in your car. And so this is why electric cars have a very short range and take a really long time to recharge. And so they can be useful if you know that you're going to drive less than 40 miles that day. And then they work. They'll work fine. But if you're uncertain how far you're going to drive, and you need to drive further than the range, it's just going to take you a very long time to recharge. That's why we're not driving electric cars. What about ethanol? You know, in the winter, the sign on the gas pump says up to 10% ethanol in the gasoline, and it's touted as this wonderful thing for the environment that we're replacing gasoline with ethanol. And there are lots of arguments over, well, how much energy does it actually take to produce the ethanol? I'm not even going to get into that. That's complicated. I'm not going to worry about it. Let's just say that we wanted to replace all of our gasoline with ethanol, assuming cars could run on 100% ethanol. How much land would it take? Well, I mean, you can figure, gee, I can grow this many bushels of corn per acre. Now, that's not the approach we take here. How much energy do we consume? How much energy do our cars consume? Because we know approximately how much cropland is being used for human food, and so we can extrapolate to say how much would we need for car food. So, typical human diet, 2,500 calories a day. These are food calories. They're capital C calories. Energy calories are little c calories, and there's 1,000 of them in a food calorie. So it's 2,500 food calories, 2.5 million energy calories, 10 million joules. It's about 4,000 joules to a food calorie. Okay, typical American diet. Your car. Well, I don't know how many calories it consumes, but we figured out how much energy is in the gasoline, and we know how much gasoline the car uses. Your car uses a gallon or 2 of gasoline a day. You're putting in 10 or 15 gallons of gas a week. So 1 or 2 gallons is 4 or 8 liters of gas a day. So let's take 6 liters. 3 times 10 to the 7 joules per liter. 2 times 10 to the 8th joules. Your car uses 20 times as much energy as you do. Okay, it's no surprise. I can't propel 2 tons of metal down the highway at 60 miles an hour. The engine of my car can. So, but the point is that if we want to use corn-based ethanol to replace all the gasoline, we would need 20 times as much cropland as we're currently using. Now, I don't know about you, but I would rather use that either to feed the rest of the world or to keep that land out of production and use it for wilderness. So, ethanol is definitely not good for the environment. And all we did to get this was said, how much do we eat? How much do our cars eat? Okay. Plastic water bottles. A colleague of mine came over to visit at some point, and had water with lunch, and then worried for the next 10 minutes, where can I go to deposit this plastic water bottle to get it recycled? Because it was really important to him to recycle it. Well, the question is, how much should you worry about it? Well, what's the worth of a plastic water bottle? How would I figure that out? Well, plastic is made from oil. It's a hydrocarbon. And so it contains energy. And it contains, well, we know how much energy gasoline contains. So let's assume that plastic has the same energy density. If anything, plastic will be less, so we'll overestimate, but that's good. So its energy content will equal the energy density, little e, times its mass. And the mass of one of those plastic water bottles is not much. It's more than a paperclip. Paperclip has a mass of about 1 gram. It's less than a few ounces of water. So we'll figure more than 1 gram, less than 100 grams. Geometric means about 10 grams. So, okay, 10 grams. And we know that it's 4 times 10 to the 7 joules per kilogram. 10 grams is 10 to the minus 2 kilograms, because there's 1,000 grams in a kilogram. Multiply it out, I get 4 times 10 to the 5th joules. Well, that's 1/100th. That's the energy of 1/100th of a liter of gasoline. Liter of gasoline, well, a gallon's about $3 or $4. A liter's a quarter of a gallon. So a liter of gasoline is about $1. It's 1/100th of a liter. It's a penny's worth of energy. Another way we can look at it, we can convert it to kilowatt hours, because we pay for electricity in kilowatt hours. 400,000 joules. 1 hour is 4,000 seconds, so that's 100 watt hours. 1/10 of a kilowatt hour. Kilowatt hour will cost you about 10 cents. So it's about a penny's worth of electricity. So that plastic water bottle, after it's been transported, cleaned, collected, sorted, and processed, might have a value of a penny. Remember, landfill space is not a problem. So if you want to recycle that water bottle, go ahead, but it's not worth worrying about. I mean, at home, I've got the recycle bin right next to the trash can. It's really easy. The recycling goes here, the trash goes there, no problem. If I'm away from home, I don't care. It's not worth my time to worry about a penny. If you wouldn't stoop to pick a penny off the sidewalk, don't worry about whether or not to recycle that. Why does this matter? Well, we all have a limited attention span. We all want to be good people. In general, people, once they've done a certain quota of good deeds for the day, stop worrying about whether or not they're good, which is why you have people driving their SUVs to the organic food store. And, we're humans. And so if you spend your good deeds, if you waste your good deeds recycling plastic water bottles and feel really proud that you've recycled your plastic water bottles, therefore you've done your bit for the environment, no, you haven't. Do something else. So which gets us to the most frequently asked environmental question of our day. You go to the grocery store and they ask you paper or plastic. Okay, let's start with the reusable bags. Emergency room admissions for poisoning went up when they banned plastic bags and people started using reusable bags because they don't clean them. And so there were a lot more infections. This was bad. So let's stick with disposable bags. So paper or plastic? Well, how many plastic bags do you use? I mean, let's look at the impact. Go to the grocery, get 10 plastic bags. More than one, less than 100. Go to the grocery store twice a week, get 20 bags a week, times 52 weeks, 1,000 bags a year, 300 million Americans, there are 300 billion plastic bags. Oh my gosh, that's a horribly huge number. Well, anything multiplied by 300 million is a huge number. So we have to compare to something else. Let's compare to our major use of hydrocarbons. Again, plastic bags, they're made from hydrocarbons, so they're made originally from oil. Our major use of oil is burning it in our car. So let's compare the weight. So how much does one plastic bag weigh? I don't know. How do you weigh a plastic bag? It's so big and flimsy, but I can estimate the weight of a roll of plastic bags, and that roll of 50 or 100 bags is going to weigh a few ounces. So I'm going to get about 200 bags in a pound. So my 1,000 bags will weigh about 5 pounds. Okay, so I'm using 5 pounds of plastic bags in a year. That 500 gallons of gasoline you burned last year at 8 pounds a gallon weighs 4,000 pounds. There's 1,000 times as much hydrocarbons consumed in the gasoline than there is in the plastic bags. Again, the difference between a factor of 1,000 is a sip of wine in 30 seconds or a bottle of gin in all night. A factor of 1,000 is huge. So don't worry about your 1,000 plastic bags. Just don't let them fly off in the wind. They don't look very good as on trees and in the water. But as long as you throw them out, and everybody here will, I know, it's not an issue. So the real answer to the question of paper or plastic is who cares? It's not the important issue. So the other thing we can look at is windmills. This will also get a little complicated. So how much power can a windmill produce? Well, what does a windmill do? Well, a windmill takes the kinetic energy of the air blowing past it, and it converts some of it to electrical energy. Well, how would I figure out how it does that? Do I have to worry about the shape of the blades? Do I have to worry about the configuration? No. What it's going to do is it's going to convert more than 1% of that kinetic energy and less than 100% of that kinetic energy into electrical energy. So the efficiency is between 1% and 100%, and we'll just say it's 10%. So now what we have to do is estimate the kinetic energy of the air passing through the area of the windmill. So the air mass divided by the time, m over t, will be the density of the air times the velocity of the air times the area swept by the blades of the windmill. So it's not just the area of the blades themselves, but it's that whole circle. So the power is the kinetic energy divided by the time. Kinetic energy is 1/2 mv squared. Divided by the time, there's that m over t that we've got here. And so if I replace m over t in the right-hand equation with the density times the velocity times the area, and I multiply by the efficiency, so it's got the efficiency times the kinetic energy over time. The efficiency is 0.1 times 1/2, density of air, velocity of air, area of the blades, and then v squared of the air. Notice that the power goes as the velocity of the air to the third power. So if the wind speed doubles, the power goes up by 2 cubed, which is a factor of 8. If the wind speed drops by a factor of 2, the windmill is putting out 1/8 as much power. Very variable. Okay, how big is the area of the blades? Well, it's more than 10 meters. It's less than a kilometer. So we'll say that the blade span is 100 meters. I'm not going to worry about pi r squared. I'm just going to take 100 meters times 100 meters. So my area is 10,000 square meters. Let's take a 20-mile-an-hour wind that's 10 meters per second. Yes, if you're in your science classes, they do things in meters per second. Multiply by 2 to get miles an hour. And then you go from this weird science unit to something you're used to day to day. So 10 meters a second is about 20 miles an hour. So now we just put in the numbers, 5 times 10 to the minus 2, which comes from the 0.1 times 1/2. The density of air is 1,000 times less than the density of water, so it's 1 kilogram per cubic meter. 10 meters per second cubed, that's our wind speed. There's the area, 10 to the 4th square meters. We get 0.5 megawatt, 500,000 watts. Okay, great. But that's if the wind is blowing at a steady 20 miles an hour, which it doesn't usually. And so that means that we've got to be prepared when the wind speed drops to replace that power. That's the big problem with wind power, is you've got to have backup power for it. So how many windmills would we need? Well, how much power does each of us use? We each use a few kilowatts of electricity because you've got a few 100-watt bulbs, and sorry, they're outlawed now. You've got a few light bulbs, you've got a refrigerator, you've got your heating and cooling system. Averages out to about a few kilowatts per person. So we've got 3,000 watts times 3 10 to the 8th people gives about 10 to the 12th watts, 1 terawatt of electricity that we use. If we want to replace it with windmills, 10 to the 12th watts, 500,000 watts per windmill, we need 2 million windmills. The wind's only available 20% of the time, then we need 10 million windmills. That's a lot. A typical coal-fired or nuclear power plant is about a gigawatt. So it's about 1,000 times more energy, more power than one windmill. So you need about 1,000 windmills to match one power plant. But when the wind's not blowing, you have to store the energy somewhere. Where do you put it? Well, the only energy storage medium we really have is batteries. Uh-oh, we're going to need a lot of batteries. So for each day, 10 to the 5th seconds, 10 to the 5th seconds times 10 to the 12 watts, we have to store 10 to the 17 joules of energy. We figured that there were a few 100,000 joules per kilogram for batteries. That's our battery energy. That M here is mega, so 0.3 megajoules is the same as 300,000 joules per kilogram. That means dividing 10 to the 17 joules by 300,000 joules per kilogram, we need 300 billion kilograms of battery, about 3,000 aircraft carriers worth. Aircraft carriers, 100,000 tons, which means that we need another $10 trillion of batteries. So wind might be part of our energy solution, but it's never going to be the entire answer. It's just too variable. And we just are... Look, we all know batteries are horrible because we all have to recharge our cell phones and laptops and everything else every day. So we don't have the battery storage technology. Okay, let's talk about a much more applicable problem. If the sun were made out of gerbils, the Earth would be incinerated. Let's compare the power density of the sun and a mammal. Well, the mammal we know best is us. So we already worked this out. We consume 2,500 food calories a day, 4,000 joules per food calorie, which gives you the 10 to the 7th joules per day. There's 100,000 seconds in a day. Multiply this out, we get 100 watts. So the heat output of each of us is 100 watts. Architects and engineers take this into account when they're designing the heating and cooling systems for buildings, and especially for auditoriums where you have lots of people. So in round numbers, mass is 100 kilograms, about 200 pounds. That means that the power from a person is 1 watt per kilogram. Okay, let's look at the sun. How do we get the numbers for the sun? Well, we get the numbers from the sun from two places. The first is that solar energy at Earth orbit is about 1,000 watts per square meter. And so if I take that 1,000 watts per square meter and multiply it by the area of a sphere, the size of the Earth's orbit, that would capture, if I could make a sphere the size of Earth's orbit, I would capture all the power coming out of the sun. So the area of that sphere is 4 pi r squared. The distance to the sun is 150 million kilometers, or 150 billion meters. And so I multiply this out, and I get that the power of the sun is 3 times 10 to the 26 watts. If I want the mass of the sun, well, you can Google it. You can also use the orbital period of the Earth. I'm not going to go into it here. But the mass of the sun is 2 times 10 to the 30th kilograms. So the power divided by the mass, 10 to the 26, divided by 10 to the 30, 10 to the minus 4 watts per kilogram. Each one of you has 10,000 times the power density of the sun. So the next time you're feeling powerless, just remember that. Now, why is it so low? I'm not carrying all the food I'm going to need for the next 10 billion years. The sun is. So it's not really a fair comparison since the sun is carrying all of its fuel for the next 10 billion years, and in fact all the fuel that it's burned in the last 5 billion. But we've got 10 to the 4 times the power density of the sun. If the sun were made out of humans, it would be put out 10,000 times the power for a very short period of time. And the temperature of the Earth would not be 70 Fahrenheit, or it would be much closer to 5,000. That would be most uncomfortable. Gerbils, by the way, consume more energy, more food than we do per mass, give off more energy than we do per mass because they're a lot smaller and they've got less insulation. They're a lot more active. And so if it was gerbils, it would be even worse. Gerbil power, absolutely. So if the sun were made out of gerbils, the Earth would be incinerated. Okay, next thing we can look at, we've been looking at energy. Well, we had a near miss. Well, I don't even know if you'd call it a near miss. We had a near hit over Russia last week. And so how much energy do these asteroids carry? Well, let's think of a 1-kilometer asteroid. To figure out how much energy it has, we would need to estimate its mass and its velocity. Let's assume the worst case, it's an iron asteroid. So its density now is 10 tons per cubic meter. No, I used the exact number there, 8 tons per cubic meter. I don't care. The size is a kilometer, 10 to the 3rd meters, And I'm just going to say it's a cube. 10 to the third meters by 10 to the third meters by 10 to the third meters. It makes the math easier. I don't care if it's a sphere or a cube or whatever. So I get a mass of about 10 to the 13 kilograms. How fast is it going? Well, there are two ways you can think about it. You can think of it falling in from infinity to hit the Earth, in which case it's traveling with escape velocity from the Earth, which is about 11 kilometers a second. I was a kid during the Apollo program. I remember that number. Or you can say, well, it's got about the same speed as the Earth does, that because it's falling in from around the sun, that it's due to the gravity of the sun. The Earth's velocity as it travels around the sun is also due to the gravity of the sun. So it's about the same speed as the Earth. Well, the Earth's speed we can calculate. It's 2 pi r, where r is the distance from the Earth to the sun. It's at 150 billion meters. 2 pi r divided by a year. And so you've got 2 pi times 1.5 times 10 to the 11th meters. I didn't calculate it here, but you can 365 times 24 times 60 times 60 gives you about 3 times 10 to the 7 seconds. If you actually work it out precisely, it's 3.15 times 10 to the 7 seconds. So I just remember that it's a pi. But of course, the important number is the 10 to the 7. That's 7 there. So you work it out. The Earth is traveling in its orbit around the sun at 30 kilometers a second, 30,000 meters per second. So now kinetic energy, 1/2 mv squared, 0.5 times 10 to the 13th kilograms, 3 times 10 to the 4th meters per second squared, gives you 4 times 10 to the 21 joules, which is 10 to the 6 megatons of TNT. How much is a megaton? Megaton is 4 times 10 to the 15 joules. Yeah, I know. Sorry about that. It turns out, actually, that TNT has about 1/10 of the energy density of gasoline. Why is this? TNT explodes. Well, TNT contains all the oxygen it needs to explode. Gasoline has to bring in oxygen from the outside air. So the energy density of gasoline is 410 to the 7 joules per kilogram. So the energy density of TNT is 4 times 10 to the 6 joules per kilogram, which makes it 4 times 10 to the 9 joules per ton, which makes it 4 times 10 to the 15 joules per million tons of TNT. And so, million megatons of TNT. Make a bit of a mess. Okay, so what have we learned? Well, the first thing is when you estimate, you've got to be imprecise, because if you get caught up in the details, you'll never get anywhere. You notice that lots of time I just said, well, it's more than 1%, it's less than 100%. That's great. I don't need to know the details. So you want to estimate to within a factor of 10, estimate lower and upper bounds and take the geometric mean, which just means taking the average of the powers of 10. Break up the question into smaller pieces if you need to. Remember a few key numbers. I did most of this in the metric system because converting from watts to joules to kilograms to whatever is much easier in the metric system, and I have to remember a lot fewer conversion constants. On the other hand, I do have to remember how to go back and forth between metric and US customary units. So what did we find out using estimation and without relying on any experts? Okay, there's me, but you can repeat these calculations for yourself. Landfill space is not a problem. Batteries suck, but we already knew that. Burning ethanol in cars is a really, really bad idea. You won't save the world by recycling plastic water bottles. Paper or plastic is irrelevant. And if you see a large asteroid coming, duck. Thank you very much. So, any questions?
Well, you basically crushed all of the alternative energy things, so now what do we do?
I've crushed all the alternative energy things, so now what do we do? Well, one of the things that's happening is that the cost of wind power and the cost of solar energy have been dropping steadily with time. At some point, they'll get cheap enough that we'll be better off using solar energy rather than fossil fuels. But until such time as it gets cheaper, we're going to keep using fossil fuels. So there'll be a transition once that price changes. The other thing is that longer term, I think that what we want is we want a mix of nuclear energy, fossil fuel energy, and when it becomes cheaper, solar energy. And maybe the way to do it with solar energy will be to have an orbiting solar power satellite. Of course, to do that, we need a cheaper way to get into space.
You know, I've heard that if every house in the United States replaced one 60-watt bulb, incandescent bulb, with one LED light, we'd save millions and millions and millions of dollars.
If every house in the United States replaced one 60-watt bulb with one miniature fluorescent light, we'd save millions and millions of dollars. You're absolutely right. The problem is that our gross domestic product is $16 trillion. And so a million relative to a trillion is a sip of wine compared to 80 cases of gin.
I know, but ultimately it has to happen, regardless of the cost.
Right, but the problem is that we need to do... So what are the big things we should be doing? Live closer to where you work so you don't have to commute as far. Telecommute. It's a lot cheaper to send electrons than to go yourself. Buy the least expensive car that you're comfortable with. Some people need, some people need the storage space of an SUV, some people don't. Buy the smallest house you're comfortable with. One of the things that I did was when I replaced my heating and cooling system, I replaced it with a water-to-air heat exchanger, which is the most efficient heating and cooling system you can. So I think the point there is that the big decisions you make, the capital decisions, what car you buy, what home you buy, how you insulate your home, those are the important ones. And so adding insulation makes a bigger difference. It is good to replace the incandescents, but the problem is that the compact fluorescents contain mercury, so there's a trade-off there. And with some people, they don't like the light. On the other hand, LED bulbs are getting cheaper. So.
I've been involved in passive solar housing.
Mm-hmm.
Okay? And in France some years ago, a community built a massive solar furnace that provides all the energy for the community, totally.
Passive solar is great and can really reduce the energy you use. Active solar is not cost effective yet. In 5 to 10 years, it probably will be. Back there? Yes?
When you're doing an analysis or presenting a score analysis, what's the danger in being imprecise when you use this method to either simplify the complicated or try to convince someone something's a good idea or a bad idea?
So what are the dangers in this approach? There are, I think, two dangers. The first one is, in all the cases here, what I've showed you is the answers were always either really too big or really too small, and it was obvious what you should do. So if the answer's in the middle, then you've got to do more work, and then you really have to figure out, is it worth your while? The second danger is frequently we assume that the system is what we say is linear. One person on the diving board dips 6 inches. 2 people on the diving board dips 12 inches or a foot. If I put 20 people on the diving board, it's probably going to break. And so when you're doing estimates, you have to realize that in some cases your system's going to break and that you can't just make that linear extrapolation. You have to realize where your model will fail. And so that's definitely a concern. But
So where's the limit when you apply this? I'm saying, what do you use this for is a good idea, and when it's not a good idea?
in general, it's a good idea because what this does is this gives you your first answer. And then you look at that first answer, and then you refine it. So, and in a sense, in one sense, it's a difference between a scientist and an engineer. I can look at something, come up with a first answer, and say, yes, this can be done. And then I'll turn around to an engineer and say, you refine the idea, you do it. Yes?
Do you use the same method to do the grading for your students?
Do I use the same method to do the grading for my students? I need to get well within a factor of 3. However, one thing I will say about grading, I'm an experimental physicist. So I realize that any measurement I do contains an uncertainty. A test is a measurement of a student's ability. It's uncertain. And you have to recognize that when doing the grading.
You were talking about the gasoline Now, if you use a car with a smaller engine displacement, instead of like an ordinary 2-liter, why not just use like a 500 or a 100 cc engine car? Why not have a smaller engine instead of the bigger?
So the question is, I talk about a gasoline engine. Why not use a smaller engine in the car? It will be more energy efficient. The answer is absolutely. And one of the advantages of hybrid cars is that you can use a smaller gasoline engine, and so it's significantly more fuel efficient. What you want to do with a car is, unless you're absolutely sure that gasoline has a much greater environmental impact than batteries, is typically you want to choose a car that has the lowest operating costs. Because the advantage of measuring it in dollars is that dollars includes the cost of the gasoline, the cost of building the car, the cost of the raw materials for the car, and so it lumps it all into one package. And so the car with the least expensive lifetime cost is probably the one, I say, with the least environmental impact. And so absolutely, hybrid motors are really good. They're a tremendous advance in engine technology, and they allow you to have much greater efficiency. On the other hand, they're a tremendous advance in engine technology. Any advance in car engine technology can either be used to make more powerful engines or more efficient engines. We're humans. This is unfortunate. We tend to prefer more powerful engines. And usually what happens with hybrid cars is that you get a mix. You get a slightly more powerful engine that's a bit more efficient, that's more efficient than it otherwise would be. Yeah. So, other questions? Yes. It's a presentation online. Steve?
It will be.
It will be.
What was that?
Where?
It'll be on YouTube.
Okay. And if anybody's interested in any of my books, I have a few copies here that I would be willing to part with.
If there are no further questions, we thank Dr. Weinstein again for the talk.